Hello, in this video I will show you how to automatically perform a DFT test for energy cutoff and gas spacing in VASP using Bash and Python script. The scripts and the corresponding written tutorial is available on the implant team website. The link is here and the codes are on the GitHub. Okay, so let's download the codes. I will open the link here and navigate to the main folder and download this code using git clone. It's done. So now I can navigate to this main folder, and inside this folder are two subfolders. One is for the energy cutoff test, ecut, and the second one is for gas spacing test, k-points. And before I will show you how to perform these two tests, let's talk about prerequisites to run them. So of course you need to have Bash and Python, and then the scripts are using Py4VASP to obtain the crystal information from the postcard file, specifically the lattice parameters, which are necessary to calculate the gas sampling corresponding to the given gas spacing, and the number of atoms is also obtained as the information from the postcard. The Py4VASP can be installed using pip, and also it requires to have the VASP compiled with the HDF5 support. Okay, so let's suppose you have all the prerequisites and know how to perform the ecut test. So I will navigate to this folder, and here I have two main scripts, this one and this one. So in order to run this ecut test, I would need to copy these two files into my folder where I prepared 4 input files for VASP. I put already one example here. Specifically, it's a supercell of BTO cubic one, and I don't need to put these two files into my VASP input files. I can specify the VASP input path, the path to the VASP input files in this ecut script. So there is user settings which I need to change. It's only in this Bash script. So I will open the Bash one, and the user settings is here. So I can define the path to my VASP input files, or I have it in the same folder where I have this script. Then I need to set the maximum ecut setting. To be quick with the computation now, let's just set it as this lower value. The minimum tested ecut parameter, so let's say in this example like 300, and the step between the ecut, so let's say 50 electron volts, and then I need to set the number of cores I want to use for the VASP calculation. So in my case I will use 6, and the name of my VASP binary, and for me it's this one. So I will save this, and I need to give this Bash script executable rights. So that I will do with this command. Okay, now it's executable, so I can run it. And the output from this will be a new created text file, which content will look like this. I will actually show you here. Sorry, just navigate. Where is this one? Here. Ecut test, and this file newly appear here. So if I open it, it mentions the set current, the current ecut parameter, the total simulation time it took to compute for this parameter in minutes, then the total energy, and this one, the first value, is set as the as a baseline value to which all other lower ecut parameters are compared. So this is the energy difference between this baseline energy and the current ecut energy. So this one is this minus this, so it's 0, and it's energy per atom. So I can refresh it now. Yeah, and I can see this, the difference, the energy difference per atom between the ecuts. So the reasonable one that I would like to set could be the difference of 1 millectron volt, which is in this case, let me refresh for the last value. So it could be this 400 electron volts, but I set for this example kind of low upper value of ecut. I should set something like 900 or 1000, and that should be my baseline to which I should compare all lower ecut values. Okay, and also this script created automatically the plot. Let me open it, and this plot shows two information. One is the energy difference per atom depending on the energy cutoff, so it's this blue line, and again I can immediately see that in this example case, which is artificial, I recommend to set a much higher upper value of ecut. I could set as the reasonable one cutoff which has the threshold of 1 millectron volt per atom as 450 electron volts, and also it shows a second chart, this image, and it is for how much each ecut, how much time, total simulation time, each ecut took to calculate. Okay, so that's how to run the energy cutoff test. Okay, so now let's illustrate the K-sampling convergence, how to run it. I will navigate to its main folder, the k-points, and inside this folder I have 3 main files which are necessary for this convergence test, and 2 Python files and 1 bash script, inside which I need to set again the user settings. And as before, I have here the same VASP input files for the same BTO example. Okay, so let's open the K-sampling, and the same here is the directory path. So it's the current directory because I put the VASP input files and mine 3 scripts to the same folder. Then the minimum K spacing, which corresponds to the best settings. So let's set it like this. The maximum K spacing, which is the worst settings. the step between two consecutive car spacings, and my specific number of cores to use for the calculation, and the VASP binary, which in my case it's this one. So I save this, close it, and again this is already executable because I tried it before, but if I just download the code, I need to make this executable with this command. So now I can run it. I can run it, and while it's running, you can see it automatically calculated the car spacing corresponding to the the car sampling corresponding to the best set car spacing. And while it runs, the code automatically calculates this correspondence, and it rounds the numbers like this. So everything which is above 0.4, for example, if the K1 sampling will be 3.42, this K1 parameter will be set as 4. If it will be as 3.39, then it will be set as 3. And everything below number 1 of the K1, K2 or K3 will be rounded to 1. So for example, this value will be set as 1. So the script is running from the best settings to the worst settings, and it will take a lot of time. We will not wait for that, but once it would be finished, or once at least one tested parameter will be finished, it will create a output file which look like this. Let me increase it like this. So here I have the current tested car sampling. The first value is the best value, which serves as the baseline to which all energies corresponding to the lower car sampling are compared. Then I have here the 3 parameters of the car spacing of the Monkhorst-Pack grid, the total simulation type corresponding to the settings, total energy, and the energy difference between the baseline energy and the current tested car spacing. And so if some car sampling will be the same for the car spacing, it will just be skipped and the values will be copied from the step above, which has the same settings. And and this also will create a chart. Let me see it here. So this one. So it's create dependence of the energy difference per atom for each car spacing compared to the best the set car spacing. And there is again a second graph which is the total simulation time for each car spacing. So in this example, which is illustrated here, I could set as the reasonable car spacing or car sampling, for example, this value 2 times 2 times 2. The better one could be 4 times 4 times 4, or I can also set 3 times 3 times 3. Okay, so this is all, and I illustrated how to use these Bash and Python scripts to perform energy convergence tests for ecut and k spacing in VASP. Thank you for your attention. And I forgot to mention one thing. So the k sampling corresponding to the k spacing is calculated using the lattice parameters, and it truly takes into account the lattice parameters, which in the previous case it was the cubic structure, so k1, k2, k3 were the same. But if I have a structure, for example, like this one, where the C parameter, lattice parameter, is much bigger than the A lattice parameter, the K sampling will take it into account. So if I just modified the code to avoid, or actually to avoid running the VASP simulation, and if I just run it, and I already converted into Postcar this structure, so I can stop it. Of course it gives me errors, and I can see that the K sampling, which corresponds to the K spacing of 0.02, is 11 times 11 times 4, which is in correspondence to that the C lattice parameter is 13 angstrom, and the A and B lattice parameters are 5.4 angstrom. Okay, so thank you again for the attention.